these system design questions. Design Facebook's post search. I'm on Hello Interview, a website. Let's select senior level. Design Facebook's post search. The functional requirements are users should be able to create and like posts. Users should be able to search posts by keyword. Okay, so we're creating, we allowing users to like posts, search by keyword. And users should be able to get results sorted by recency or like count. Okay, the scale of the system is 1 billion daily active users and 1 trillion posts. Constraints are we don't want to use engines like Elasticsearch or pre-built full text index. Okay. Yes, that will be the main difficulty. We essentially, I think, are asked to design something like Elasticsearch. Okay. Those are non-functional requirements of the system. Update your design if needed and design how the changes answer the question. Okay, so from a non-functional point of view, we definitely want a system which is so one of the first things which we usually need to decide is if we want a system which is highly consistent or highly available. Now it also may depend. Some parts of the system may be highly consistent, other parts of the system may be highly available. So when it comes to creating, liking posts, so when it comes to well, essentially liking posts, I would say that part would be highly available. Creating posts, well, in terms of CAP theory, I would say we want to be either highly consistent, highly available. I think processing capability in this in context of Facebook post search would be better from also business perspective. Yeah, if it was banking transactions, that would be different, yeah, because banking transactions, if they're not highly consistent, then the trust from our users would get lower. Users should be able to search by keyword. I would say also highly available. Usually, if we miss some posts, if we're searching on the replica, which is not yet up to date, then usually it's okay. But in certain systems, if we are looking for, we were designing search system for something which needs to be much more accurate, then we would decide on high consistency. Users should be able to get search results sorted by recency and like count. So similarly, so pretty much I would say that system be highly available. Available. We when it comes to creating and liking posts, we want all those interactions to be relatively fast. Yeah? If user creates posts, we want that to be created relatively quickly when we liking posts. We don't want to wait for that too much. So I would say like we want system to be fast and durable. Durable because if we're creating or liking the post and let's say we're coming back after a while, to the same posts. We don't want to miss that like or that new post. Yeah, it should stay there. Unfortunately, lots of systems are not highly durable. For example, WhatsApp, like it seems to be missing messages from time to time. Yeah, but that would still be a different topic. And I would say, yeah, well, we usually want a system which is also highly scalable, especially as we can see by system scale part, we need to deal with billions of daily active users, trillions of posts. So one system would be scalable to handle that kind of load. And it's a more professional way of saying fast is latency low. Instead of saying fast, we can say that we want system to provide low latency. Yes, I would say those would be sort of main points. Yeah, let's see. Let's run the judge. Okay, we are on the right track. If you identify some important non-functional requirements, including consistency considerations, availability, latency, durability, and scalability, what needs improvement? You mentioned of CPU versus AP touches on consistent models, but should be more specific for this system for Facebook post search system. Eventual consistency would be appropriate as it enables better scaling while allowing some delay in search results reflecting the latest post. Okay, so that's actually what I was explaining, just I didn't write it down. In the context of CAP theorem, CP stands for consistency and partition tolerance, while AP stands for availability and partition tolerance for a system like Facebook post search, prioritizing availability and partition tolerance with eventual consistency is often more beneficial as it allows the system to remain responsive and scalable during network partitions. This approach is crucial in interview setting because it demonstrates your understanding of how to balance trade-offs in distributed systems to meet specific business needs. As non-functional requirements, releases are quite general and benefit from contextualized, from being contextualized the Facebook post search system specifically. For example, instead of just saying scalable, consider what specific scale this system is to handle the number of users. So I didn't write it down, but I pretty much that's what I explained. When you specify non-functional commands, it's crucial to tailor them to the specific challenges and needs of the system you're designing. This helps demonstrate your understanding of the system unique demands and shows that you can prioritize effectively. In an interview, this specificity can set you apart by highlighting your ability to think critically about the system's requirements and design solutions to meet them. When mentioning low latency, consider specific context of search operations. Users expect search results quickly and slow response negatively impact user experience. Yes, that's again something which I explained in context of specific low latency for search operations means setting clear targets such as response time of 500 milliseconds or less. But to ensure smooth user experience, this typically helps guide design decisions, ensuring that the architecture supports quick data retrieval and processing. In an interview, demonstrating this level of detail shows your ability to tailor non-functional requirements to systems' unique challenges, which is crucial for effective design. Consider quantifying your requirements where possible. For example, specify target response time for search queries, search results within 500 milliseconds. Okay. Quantifying requirements helps set clear expectations and provides a measurable target to guide the design process. In an interview, this demonstrates your ability to think critically about system performance and ensures that your design decisions are aligned with specific goals. It also helps in prioritizing trade-offs and making informed decisions during design phase. Consider adding a requirement about how quickly new posts should be indexed and available in search results. E.g., index new post within 1 minute. Okay, that's a good point actually. Yeah, how fast we want to index new posts. Indexing new posts quickly ensures that users have access to the most up-to-date information, which is crucial for maintaining the relevance and usefulness of the search feature. In an interview, demonstrating awareness of this requirement shows that you understand the importance of timely data availability in enhancing user experience and system functionality. Okay, so that's the sample answer. This is a straightforward search system. Will ensure eventual consistency is fine and put some parameters on 1 minute so that we have a target for our design. We'll also set some latency guardrails that are realistic for a search page. Non-functional requirements, eventual consistency, index posts within 1 minute of creation, low latency for search, P90 less than 500 milliseconds. Okay, yeah. Since yeah, maybe I will update it just to practice it. Let's see. Want low latency search. So pin 95 to be less than 500 milliseconds. And indexing of new posts in less than 1 minute. Less than 1 minute from creation. Low latency for search. Yeah, we can say P90. Okay, let's go further. Now, what are the core entities of the system? Update your design if needed and describe how the changes answer the question. Okay, so core entities. So those will be user, be post, like. If we come back to our function requirements, then we can detect them essentially. So user should be able to create and like posts. We have posts, we have user. Yeah, we're searching posts and yeah, we also need to count those likes, which can be considered as a separate entity actually. Okay, let's see. Okay, don't change a thing. You must consider adding topic as optional entity that could help categorizing and searching posts through. It's not essential for the core functionality. Okay, including topic entity can enhance the system's ability to organize and filter content, making it easier for users to find posts related to specific subjects. In an interview demonstrating awareness of potential enhancements like this shows your ability to think beyond the basic requirements and consider future scalability and user experience improvements. Okay. Yeah, they didn't include topic here. Yeah, that's kind of a bit weird suggestion. This system has very basic core entities with indexing posts, which may have likes and are created by user who also might be doing the search. Okay. Okay, now API, what are the external REST APIs that your system will expose in order to satisfy the functional requirements to search posts and create like posts? Okay, on to update design. API acts as a contract between your system and users. Okay, so now we can again come back to requirements, and first requirement is that users should be able to create and like posts. So we're gonna need API for creating posts, for updating that like counter as well. So that'll be our first post endpoint post. I'm gonna create we're gonna create maybe we can call it we'll call it posts, or that might be a bit confusing name, but I think those were message would be also sort of confusing. So okay, let's go with post. I'm using here a post as a noun rather than a verb. And they'll be authenticated API call. So in the header or in the cookie, we would have our JWT token, for example. So let's say JWT, and in the body, we're gonna provide essentially user we can extract from JWT. In the body, essentially, we need let's say text, and we may also need to send like some sort of like attachments or images. They are usually displayed, I think, under the post. So because posts are rich text, so that text could be essentially some sort of JSON which describes that rich text. So those would be like main things which we need to send. Obviously, in real life, there will be more things. And we're gonna return. We can return, for example, post ID. Okay, so another endpoint which we're gonna need would be for likes. That'll be actually for updating. So we could use put for like, and we don't really need to use. We won't need to send anything in the body. It will be again authenticated. Request, and maybe in the back we're gonna return like current counting. Okay. User should be able to search posts by keyword. So that will be get request. Get. And maybe that I would say it will be yeah, I think in REST APIs it's usually plural. Or okay, let's keep it singular. And in get, and just call it maybe again post. That doesn't need to be a really authenticated request. Could be, because then we may get results specific to the user, but if it's not, then it's still okay. Um, and we'll be returning essentially array of it will be array of posts. Yeah? So and the post will have some sort of ID, text, images, updated at, created at author or created by, and so on. The post endpoint can be also paginated usually. So we need to support pagination. For that, we can allow to user to pass size and page. We could also support cursor pagination, which is actually more popular in those Facebook type of news feeds because for many reasons, but the the good uh, um, the good reason to choose cursor is that essentially with pages, if there's lots of new posts, us going to the next page may essentially repeat the same post because in the meantime there may be lots of new posts appearing. So going to the next page not going to have effect. But when we send in cursor, then it's we essentially sending we signalize our position, and yeah, in that way we can always query the relevant results. So we can also do it via cursor. So then we'll be sending cursor. Obviously on the first request, we need to send that cursor. And we can also send size for next query. That will be cursor-based pagination. Okay, and user should be able to get search results sorted by recency and like count. So again, we can provide like more options here. So we can provide another option to sort. Or maybe I will add it here and sort by likes. Sort by likes, or we can maybe do it like that. So by likes, or we can pass a recency. Yeah. So in that way, we're gonna cover all those main requirements. Let's see what our judge will tell us. Okay. Okay, we provided a good set of endpoints, including post creation, post pagination, and like functionality. API includes pagination of both page-based and cursor-based approaches. You include sort capabilities in your get endpoints, which allow for different ways to organize the feed. Okay, your API is missing a way to search posts by keyword, which is configured. Yeah, I mean, essentially we can just pass the keyword. Yeah, that's something which I forgot. Your post endpoint needs a query parameter to allow users to search through post content. This is essential content discovery. Yeah, that's something which I actually forgot. Yeah, usually we can use that kind of query parameter. Question mark q is equal to keyword. To get to enable text across in interview, having search functionality is important to demonstrate since it impacts both the data model and infrastructure choices you will make in your high-level design. Posts endpoints need some a query parameter to allow users to search for post content, but it's essential for content discovery. If you include a post ID in the path, just yeah, that'll be actually more restful way of doing that via posts and yeah, that would be much better actually. In REST, resources should be clearly identified in the URL path, and action should be performed on those resources using HTTP methods. The current design makes it unclear which post is being liked, while including the post ID in the path makes it explicit we're performing a like action on a specific post resource. This approach also follows REST best practice of organizing APIs around the resources rather than actions. Okay. Yeah, that's something which we definitely should change. We can say post ID, and then like yeah, and obviously here we need to pass keyword. Consider using a more descriptive request body for the like endpoint that clearly indicates the action being performed. Instead of just count field, the request body should include a boolean field like is liked that explicitly indicates whether user is liking or unliking endpoint. The post this makes the API more self-documenting and easier to understand for clients consuming the endpoint. In interview, being explicit about request response must demonstrate attention to API design, clarity of thought. Yeah, that's actually a good idea. Because we can use the endpoint to both like or dislike someone. So disliked. Oh, false. Okay, let's see example answer. Yes, so we need the API for searching and two APIs for creating posts and liking posts. While our system is indirectly handling storing posts and likes, we'll use these APIs as trigger points for downstream elements of the system. Okay. Yeah, that's the get endpoint. It's also versioned. Posts, and we sort by we pass our keyword and page size, and there'll be cursor. We return post and next page token. Yeah, that's also a good point. And here we have posts, also version, and posts, and we return content of the specific post, and for likes. Well, they actually they don't do that under posts, which probably would be better. Although technically in Facebook you can like also not only posts but other things, so it kind of depends. But yeah, they think versioning, that's kind of nice thing to put there to show that you're thinking about versioning, very important part of development. But another thing is like we're gonna return posts, and with cursor-based paginations, we also need to return next cursor. So yeah, I'll update it here. So I'll return return our posts. And we're also gonna return the next cursor. We could also return previous cursor and other things. But often, you're gonna see actually gonna see a pagination info being returned. Info. But that will be especially for I don't know if it's returned usually for cursor-based paginations. I think it may go both ways. But very often you can see pagination info, and then it would say the size and current page, and it would say also if it's the last page. That's something which you're gonna see more with regular page-based pagination. Okay, let's see what's next question. Okay, how will we users create posts and like them? Draw a simple diagram on the board and explain how it answers the question. Okay, let's do it. Let's allow it. So again, we want to have a simple diagram for creating and liking posts. So we're gonna start with UI. So that will be our UI, our wall or newsfeed. And that newsfeed will have essentially either some sort of input box, or it will have our like buttons. And when user clicks on them or provides them content for the post and clicks on create post, that will trigger essentially one of the calls to our backend. And usually to make the system scalable, we want to use some sort of API gateway. And to our API gateway, we're gonna delegate a bunch of tasks which need to happen for every request. So we can delegate to our API gateway things like load balancing, things like SSL, things like authentication, lots of like security things. Yeah, load balancing, SSL authentication. Okay, and then after that, it's gonna hit our service, which we're gonna have, let's say, one that system be scalable. So we're gonna separate those concerns. So we're gonna have one service for likes and the other for posts. It's called post creation and likes service. And essentially, yeah, each of them will need to update either shared or separate database. Okay, let's quickly finish that. So we're gonna have our database. And yeah, here you're going to store our posts, and they're gonna have our ID created at created by content and other properties. And in our like service, so we could technically we could store our likes under the post, but because the likes will be probably 10 or 100 times more happening, hundreds or if not thousands times more than post creations. That's why it would be actually good to separate that. Yeah, so we don't we don't abuse that DB. And here we can store our likes, and we can store either like the likes as a like each as an event, which may be useful. So that'll be again very similar properties we're gonna need created, add, and so on. But then that is gonna cause some problems because then we need to count them if the user needs them. So for that, kind of, we need to think about some further solutions. Your design includes important infrastructure components like API gateway that handles cross-cutting concerns, load balancing, SSL cross-cutting concerns, like SSL authentication. You correctly identified that likes would occur much more frequently than post creation, justifying the separation of these services. The base schema includes the essential fields needed for both post and likes. Okay, and we want to consider adding reference fields in the likes table or to track both the post being liked, post ID, and the user who liked it, which would be necessary associating likes with a specific post and user. Yeah, of course we can add here more things. Without them, these references, we won't be able to answer basic questions. Yeah, that's true. Yeah, post like, okay. So actually that's very similar. Let's keep it simple. Create two services for posts and likes and route to them. Okay, makes sense. Now, how will users be able to search by keywords? Start simple, we'll optimize it later. Okay, so let's start it. So again, user would be on our newsfeed. User would load that newsfeed. Then we need to, yeah, in the newsfeed, gonna have some posts, most recent post, but on that UI, we will want to also have some sort of search feature. So user will enter in their keyword. We will be using our get endpoint. Again, it would hit our API gateway, which deals with those cross-cutting concerns. And we would use our endpoint for cursor-based endpoint. Okay, and then so we have like a separate service for creation here. So now that's the query operation. So to keep that system highly scalable, we again going to have a separate service for querying posts. Yeah? So we can call it search post service. And now in the most basic way, that would essentially just query our database and we can search on our content column and return the results which have that particular keyword. But now that will be obviously very heavy, but that's something which we can start with, and yeah, we're gonna optimize that later. Okay. Okay. so you create a clear separation of concerns with dedicated services for different functionalities. Post creations like service, a search post service. Your design includes a proper API gateway to handle cross-cutting concerns like load balancing, SSL, and authentication. You correctly identified that keyword search can start with a simple implementation querying the content column in the database, acknowledging that optimization would come later. And there's a discrepancy in your diagram where to search post service connects to itself rather than post database. Yeah, because I wanted to mark that we're gonna, it's gonna return return post from the database product to show service query. In a high level, a design diagram connection should accurately represent data flow between components. And search post service needs to query the post database to find content matching the search keywords. So this relationship should be clearly shown with an arrow from search post service to post database. Clear and accurate connections help interviewers understanding your design's data flow at a glance. Okay. Yes, they just added search service directed to post database. We're going to add a search service as an endpoint handling search requests. We'll assume for now that we can simply search the post DB, but we'll probably note to our interviewer that this obviously won't work at scale. We'll get back to it later. Okay. How will users be able to sort their results by recency and like count? Okay, so provide again user on the UI side, we can provide users with sort by button, and that would can technically we could sort it on the front end, at least to some extent, but usually we would make another request, and we would in the sort by recency or count, and then in our search post service, what we can do is we can essentially run a query which counts the well, either counts likes or sorts our results by recency. To do it in kind of for recency, to do it in sort of like easier way or faster way, it would be good to have created that or updated that as a sort key. So in that way, we're going to keep our results sorted. Yeah. In that way, that query will be faster. But now for count, so count is now stored in different database, in different table. So the query would need to aggregate, count all those likes, and that would be very heavy. So as a solution for that, those likes would be, the first solution, optimized solution would be to essentially keeping somewhere like up-to-date track of that. Yeah, we can have, for example, DB trigger, and based on that we can update maybe some in memory Redis counter and collect likes from there. Okay, I'm not using Elasticsearch or pre-built full text search. Yeah, okay, we don't use pre-built full text index. So if we don't want to do that, then we need to implement reverse indexing. I think it's called reverse indexing. So for that we would have essentially keyword, and for this keyword we would keep a list of posts like this. Let's say where that keyword existed. And essentially that's how Elasticsearch works, but yeah, we need to build that ourselves, I guess. Okay, showing straightforward approach to implementing the new requirement. You recognize the complexity levels between sorting by recency using a sort key versus sorting by like count requiring aggregation across tables. You propose a predictive optimization for like count sorting by suggesting keeping track of counts with database triggers. Okay, and consider adding a like count field directly on the post table. Yeah, that would be a second solution, a bit more optimized to avoid expensive joins or aggregation when sorting by popularity. When a user likes a post, you can increment the counter field atomically alongside creating a like record. This denormalization pattern is common technique to avoid expensive operations, read time, trading some write completely, and storage for much faster reads. In an interview setting, machine optimization shows you thinking about practical performance considerations while keeping the design simple. The reverse indexing component shown on your whiteboard wasn't fully explained in your verbal response. It would be helpful to clearly clarify how this relates to sorting functionality. In your design, you show a reverse index mapping keywords to post IDs, but it's unclear how this interacts with the sorting requirements. You should explain whether you plan to maintain separate reverse indexes for different sort orders, or if you retrieve the post IDs and then sort them afterwards. And this helps demonstrate you've thought through how the search and sort functionalities work together. Yeah, probably I would keep just IDs, because otherwise we're gonna keep like so much data here. And then what happens if user updates the post? So it's better to keep track of IDs. But yeah, like then to sort it, while we can again keep separate. They separate. We can keep them separately. Or when that keyword is requested, then we, then we need to make, then we need to check when that post was created and then return. So yeah, there are certain complexities there. Okay, let's see the example answer. To be able to sort by like count and created that, we need to be able to retrieve them. Like setup a like cache, maybe Redis, where we can cache counts from our like database that otherwise has one record per user. We'll invalidate, recalculate whenever a like happens for a given post. Okay. We have essentially just like cache, where we store account for each post. Yeah, so that's actually a solution I was thinking about, but well, here they describing a little bit different solution. They just talking about adding a new count property to that post. Okay, how can we scale the keyword search to support trillions of posts? Okay, now to support trillions of posts, essentially we'll need to create some sort of solution like Elastic Cache, Elasticsearch, and that solution is based on reverse reverse indexing, I think it's called. So we will have keyword and then we will have matching posts. Obviously, that's very simple. And that make it way more complex because keyword could be several words. Could be phrases, there could be mistakes in keywords. So that's why usually we want to use something with all those functionality to deal with all those cases like Elastic search. But yeah, in this case, that's kind of like general idea. And now we need to keep up to date that Elasticsearch. Yeah? So whenever our DB is updated with a new post, we need to also update our reverse. I don't think it's called reverse indexing. I think it's called reverse mapping or. But anyways, we need to update our Elasticsearch. So I do it on DB trigger. Yeah, that's gonna be updated here. Okay. Yes, we have trillions of posts. I'm just thinking about like other optimizations which we can do. Well, we can also do some caching, which is actually Elasticsearch supports caching on its own, but we need to recreate Elastic Cache. Elasticsearch, then we can add also some caching. And with Elastic Cache, so we're gonna need also some sort of like service or maybe Lambda, yeah, which kind of intercepts the DB trigger event and then it like updates in appropriate way our reverse index, and then our search just takes from here. That's called search optimize. Yes, that's pretty much what I did. Yeah. Yeah, we're gonna use okay. Now we correctly identify the need for reverse index structure to support keyword search at scale with keywords mapping to post IDs. Okay. Your design includes a good approach for keeping the index updated through database triggers that respond to new posts. You suggested using Elasticsearch, which is a solid choice for this use case, as it handles tokenization, phrase matching, and typo correction. While you mentioned Elasticsearch, you could elaborate on how query-side logic would efficiently retrieve and paginate through potentially massive result sets when popular keywords may match. You could elaborate on how query-side logic would efficiently retrieve and paginate massive results. Okay, for keywords, you would need to implement strategies like cursor-based pagination with efficient offset management, potentially pre-computing result pages or implementing a tiered caching strategy. You might also consider query optimization techniques like term frequency thresholds, or relevance scoring to limit result sets to most meaningful matches. In interview, demonstrating the level of query-side thinking shows your understanding not just how to store the data, but also how efficiently retrieve it while maintaining reasonable response times. Okay, yes, that's actually good points. I mentioned before cursor-based pagination, pre-computing results, result pages. Yeah, that's another thing. Implementing a tier caching strategy. Okay, you may also consider query or optimization techniques, term frequency, threshold, relevance scoring to limit results. Okay, it would be good to read more about those techniques, term frequency thresholds, relevance scoring. Okay, consider explaining how your system would handle sorting by different criteria like recency and dealing with trillions of posts. Yeah, I didn't touch it that much. I mean, I mentioned it to some extent. When dealing with trillions of posts, efficiently sorting large result sets becomes challenging. For example, with like-space sorting, you could maintain separate sorted sets in your reverse index for each keyword. Like-space sorting, you could maintain separate sorted set in your reverse index for each keyword, where post IDs are scored by like count. Similarly, for recency sorting, you could use timestamp-based scores. Like this approach allows you to efficiently retrieve the top end results for any keyword without having to sort the entire results set at the query time. Yeah, okay, so they recommend sorted sets and we sorting by likes of the post. So like instead of like array here, we would have sorted set. Okay. We've outgrown our basic solution and need to scale. We rely on reverse index between keywords in the user search and the post that match. We'll have two separate indexes. One that is pre-sorted by creation time and one which is pre-sorted by like count. We'll store this in Redis using sorted sets. Then when search happens, we can take the top elements from the index and return to the user. We'll create a separate ingestion service which will be triggered when a post is created or like happens. We'll tokenize the post, extract all the words, and update the respective indexes. Okay, we have ingestion and okay, we have keyword column. Like, okay. Okay, how would your system handle the case where a keyword like them may appear in the billions of posts? Would you reverse index design? Would your reverse index design need any special consideration for these high frequency terms? Yeah, so there are many edge cases, like the keyword might be one of them. So I mean, if user searches for them on its own, then yeah, we're just gonna show the user the result which had the most um but those high frequency so are they asking if user searches for keyword there? I mean, if it's because it's such a high frequency, then yeah, probably we can. We don't want to abuse our reverse index storage, which will be in Redis. Probably yeah, will be in Redis. So probably want to limit our sorted sets to some amount. Maybe let's say 1,000 posts. Yeah, to prevent those essentially memory leaks. Yeah, we don't store, like, we may have a situation where we store in billions of IDs for that kind of keyword. So having some sort of limit will solve that problem. And in most cases, it wouldn't affect the user. That the user is one possible consideration here. But yeah, if we set reasonable limit, then it shouldn't be a problem. Yeah, that may happen also for other keywords like a or and. Yeah, we just don't store like billions in that sort of set. So big keyword, let's say likes, that'll be our set, and yes, that would be limited. So we now how can we also prune it? That's another question. So if we store them like one by likes and the other is keyword by recency. So essentially, you prune them the starts with the least amount of likes and put our new posts there to maintain. Okay, you correctly identify high frequency terms like the posts, a special challenge for reverse index recognizing problem edge cases through systems. You propose practice solution of limiting the result set to, let's say, 1,000 posts for high frequency terms, which is a common approach to prevent memory overload. Yeah, memory overload, not leaks. In Redis or similar system, you demonstrated understanding of the performance implications by noticing that storing billions of IDs for common keywords would be problematic for system resources. Your explanation of how to determine which post to keep when pruning the result sets was somewhat unclear. You mentioned sorting by likes, but you didn't consider pruning strategy. Yeah, so we're gonna prune essentially the post with the least amount of likes. If we exceed that limit, uh, when pruning high frequency posts in reverse, you should define which posts remain in the limited set. typically either the most recent posts or those with highest engagement metrics for terms like them. It may appear in billions of documents. You may also consider specialized techniques like champion lists, keeping only the most relevant subset, or using skip pointers in your indexes. By being explicit about these pruning strategies demonstrates you've thought through the practical implementation challenges of handling common terms in production search systems. Consider adding a mention of stop word filtering as a complement. Consider adding a mention of stop word filtering as a complementary approach where extremely common words like may be excluded from searches unless they are part of multi-word query. Okay, yeah, we can possibly also filter that out, and but that not usually not gonna be the best user experience. Stop word filtering is a common technique in search systems where extremely common words like the automatically filter out of search queries because they add little semantic value while consuming significant resources. In an interview machining approach demonstrates your awareness of established search optimization techniques beyond just data structure limitations. You could explain that your system would maintain a list of these stop words and either ignore them completely or only process them when they appear alongside more meaningful terms in multi-word queries. Okay. Now how will the system handle? Okay, now how will the system handle queries with multiple keywords, e.g. Taylor and Swift, after your design? Okay. Yes, so to handle multiple keywords, and then, well, we're gonna need essentially multi-keyword, all those versions having indexed. Yeah, so we would have essentially Taylor, Swift, likes. Then our set with IDs. Again, in this case, sorted by likes. And another one we would have for recency. And that they would have like to be like the timestamp, and we would sort by that timestamp. Yeah, like essentially that's what we need to do with multi keywords here in our lambda generates and records needed is structure for reverse indexing, and especially like we may also want to include like Taylor Swift and Swift tailoring variations for empty keywords. Okay. I'm not sure if there are any like other techniques that okay, looks like you implement strong solution using bigram indexing to handle multiple keyword queries, creating pre-computed indexes. Your design includes both sorting options. Okay, yeah. You thoughtfully included a Lambda function that generates the necessary key structures for reverse indexing when new posts are created. Consider explaining how your system would handle arbitrary multi-keyword queries beyond just bigrams to word combinations. For arbitrary multi-keyword queries beyond just two words, you could implement a more general set intersection approach where you retrieve the post sets for each individual keyword and then compute their intersection. Yeah, that's interesting. Alternatively, you could use an inverted index with query. Yeah, I think it's instead of reverse index. I should call it inverted index. That's what I meant. I have query parser that supports Boolean operations, and alternatively, you could use an inverted index with a query parser that supports Boolean operations to handle complex multi-keyword queries. During the review, it's important to discuss performance implication of these approaches, especially for queries with many keywords or keywords that match with a query parser that supports multiple operations. Okay. We have to discuss the more usage implications of bigram approach, as storing all possible words combinations significantly increase search requirements. For example, if you have 10,000 unique words in your system, storing all possible bigram combinations would require up to 100 million entries. Through in practice, it would be fewer since not all combinations occur. A more efficient approach may be to store only the most common bigrams based on usage patterns and implement a hybrid solution where a computed intersection for rare combinations but pre-computed index for common multi-keyword queries. I didn't really discuss these trade-offs. Okay, that's interesting. To handle queries with multiple words, we handle bigrams like we said to store in our search indexes instead of indexing only singular words, will also index the bigrams. If bigram index is found, that would be preferred. Otherwise, the search service will need to take the intersection of two individual words. Okay, that's interesting. Okay, the OTR system handle queries with more than two keywords. Tells you concept what are the performance implication of the approach as the number of keywords increases. Yeah, so essentially we can take for multi-keyword, we can take multi-keyword, we can take intersection. So we're gonna fetch like everything with Taylor, Swift, and Concert, and try to find the words which contain all of it together, or at least we can relax to some extent actually, especially if we have less results. Yeah, and another solution would be to have also that hybrid approach. Most popular will be pre-computed, but other need to be created on the go. Yeah, because obviously we won't be able to create like every single combination. That's just gonna take the most huge amounts of memory, but we can always just keep the most important queries already ready to go and also keep them up to date and so on. Yeah, also like important thing is that those likes may change. Yeah? So recency is not gonna change, but likes may change. So that's why to keep that system quite accurate, we need to store like large amount of the most popular likes, posts with most popular likes for each keyword and keep them up to date also. That's another problem. I identified that handling all possible keyword combinations would consume excessive memory, showing awareness of system constraints. You propose a hybrid approach that pre-computes indexes for common queries while creating other on-demand, which is a practical solution for balancing performance and resource usage. You recognize that the importance of keeping the indexes updated when likes change, demonstrating understanding of the dynamic nature of the data. Consider adding specific details about how a system will perform at the on-demand intersection for multi-keyword queries that aren't pre-computed, including performance applications as a number of keywords increases. For multi-keyword queries that aren't pre-computed, you should explain the algorithm for performing set interactions, starting with the smallest set and intersecting with the larger ones. Analyze the time complexities, typically n into m, where n is the size of the smallest set and m is the number of keywords. You should also discuss potential optimizations like Bloom filters or skip lists for large sets and explain how performance degrades as keyword count increases, but potentially suggesting a limit of number of keywords in the system would support efficiently. Okay. How can we ensure such as queries are still fast in the case of many results? Okay, so to make those queries fast, essentially, we're gonna replicate Elasticsearch and we're gonna have like in-memory or search. We're gonna cache or pre-compute um, queries. Yeah, we also want to like paginate um, to ensure searches queries are still fast in case of many results. Yeah, pagination is like one of the most important. And so when we have lots of those results, then to the user we need to return not only those IDs, but we also need to go back to our post and fetch full details about that post. So that's why when we return the data to the user, we actually want to fetch the small amount of those posts, and for that we need pagination. So user will say that they need for the current page they need only 5 posts or 10 posts. It also depends on the device. Yeah, we can optimize that from the device perspective. We also want to provide actually user usually with more posts than he can describe on the page, because in some way we're reducing network costs at least to some extent, and we provide smoother experience because if you have user has more posts, the browser can render that straight away, so it doesn't need to wait for the next patch. So pagination, the most important, and probably also, like mentioned, cursor-based pagination, especially for kind of like for large system, yeah? Because in the large system for Taylor Swift, we're gonna have millions of new posts like every hour or less. So that's why in that kind of situation, cursor-based pagination really shines, because we get like uh, we get like a pointer to the database, or we point to a certain entry, and with the page-based pagination, we would, you know, like there's lots of new posts. The next page maybe, if we have, like let's say we're on the first page, and we display there 10 posts, but in the meantime 10 new posts were created. If going to the next page, we actually gonna end up with the same posts. Okay, correct. Identify the need for diverse indexing for play. So data structure for both. Okay. It's appropriate for handling large result sets and preventing issues when new content is added during comprehension. You recognize the personal limiting. A more robust multi-layer caching strategy will significantly improve performance, considering implementing both local cache within each service instance and distributed cache shared across services. This approach will protect the distributed cache from being overwhelmed during traffic spikes and provide fast response times for popular queries like Taylor Swift. Your explanation of the caching strategy could be more detailed, particularly how would you handle a prioritized caching for popular search queries? Consider explaining how your pre-sorted indexes are maintained and updated efficiently as new posts are added or existing posts receive more likes. Yeah, I don't get that. Seems to not work. The mechanism for handling intersection of multi-keyword queries for large results should be clarified, especially how performance is maintained when combining multiple high-volume keywords. Okay, let's see the sample answer. Since we're storing our posts already in sorted set in our indexes, we don't have to worry about there being millions of matches. We don't care about first and okay. To speed things up, we'll cache some search queries on a CDN so that users can get very low response times by retrieving results from the edge nodes very close to them geographically for popular queries. We can ensure CDN contains only most important search queries. Okay, so let's recommend CDN for that. Okay, so for high traffic search, terms like Taylor Swift, local cache, each service instance would store recently accessed results in memory, providing sub-millisecond response times without network calls. The distributed cache like Redis would serve as a second layer, handling queries not found in local caches while maintaining consistency across service instances. This multi-layered approach creates a performance hierarchy where the most frequent queries are served from the fastest storage medium, significantly reducing database load and improving overall system resilience during viral events and traffic spikes. So, okay, we want like a local cache in each service. For popular queries like Taylor Swift usually implement a tiered caching strategy where the most frequently searched terms are kept in memory with their pre-computed status. Consider implementing a cache eviction policy like LRU that retains popular query results longer while cycling out less common searches. Additionally, you could implement cache warning for anticipated high-volume searches like trending topics to ensure the system remains responsive during traffic spikes. Okay, the pre-sorted indexes, you should explain the mechanism that updates these indexes when events occur. For example, when a post gets a new like, how is the like sort index efficiently updated before rebuilding the entire structure? This could involve discussing incremental updates to sort of set like reduce that operation background forecast that process like event or a change data capture pattern that propagates updates to your search infrastructure in interview demonstrating this understanding shows that it maintains the problem. Okay. When dealing with multi-keyword queries like Taylor Swift, you should explain how the system efficiently computes intersections between potentially massive sorted sets. Consider discussing Bloom filters for quick elimination of non-matches or explaining how you would handle the computational complexity when intersecting large sets, e.g. using skip lists, bitmap operations to trade on this. Yeah, I need to read what uh, skip maps, and that's what we read. Okay. Okay. So how can we ensure queries are still fast in case of many results? Okay, so that's what we. To ensure. I mean, we just did. Yeah, I think the website is lagging a lot. Okay, how can we optimize the storage requirements of the system? Okay, optimizing the storage requirements of the system. Yeah, so we have our. I can't drag that. Okay, I think something is happening with that website. It's not really working very well. Yeah, that doesn't seem to be recording. Okay, I mean, I guess I will stop here. It's pretty late at night now. So yeah, that was my attempt on that question. I think it went to some extent well, to some extent. I think there's lots of things I can read up on. But yeah, I think that will be enough for today. Yeah, just that website is not working. It's lagging. That one is not recording. Okay, so I will finish here.